Hello. Today I will be going over Spring 2020 Midterm 1B Problem 2. This is a Gauss's law problem, and we're given a very long, so infinitely long dielectric cylinder. We're given all the values for A and B. We're given the values of densities, which vary with radius, and we're given the epsilon r coefficients. So starting off, you basically want to identify beforehand the regions in which the electric field has a different formula and write them out, and then you want to do them one by one. So first off, we're going to look at where the radius is less than A, so basically the blue region, where the radius is between B and A, so the gray region, and where the radius is outside the cylinder, so that's where the radius is greater than B. So we write them out, and then we go for the first one. The master equation, so to speak, is this dA, surface integral ddA equals q free inside. And typically with these problems, you right away want to write that out and then convert it to this form where you have the d field times the surface area. So for a cylinder, it's 2 pi RL. For a sphere, it's 4 pi r squared, I believe, and so on. Obviously, those aren't the only two, but those are just some examples. And then on the right side, for Q free inside, we use the volume density times dV. And we integrate that from 0 to R. We don't integrate it from 0 to A. This is a very easy mistake to make. It seems like you want to integrate it from 0 to A, but if you're integrating it from 0 to A, you're actually just finding like the constant. Well, it would still vary with how far away you are from the cylinder, but it would be like you're considering that entire region entirely right off the bat, which you don't want to do. So make sure that your bounds are always from 0 to R for the starting one, not from 0 to A. So, and that also applies later on, like when we're doing an integral from A to, like for the gray region, you don't want to do A to B blindly. It's A to R, unless you are trying to calculate the entire gray region. So the next part is we need to get rid of the dV and we need to put in a dr somehow. How do we do that? dV equals AdR, simple. The reason we need a dr is because you're not going to integrate with just the dV. It doesn't tell you anything. You need the R because you have a charge density that that has R in it. So you can't just integrate with dV and ignore that. You need to convert it to AdR. Luckily, this is very simple. The A area is the exact same as what we used for the D. The D2 pi RL, that area is the same, and it almost always is in these types of problems, whether you're doing it for a sphere or whatever. So the next step is to plug in our 2 pi RL dr and plug in our charge density for the blue region. Then we can integrate, and we have this handy dandy little equation. So now that you might be looking at this integrated expression on the right and the d2 pi RL on the left, you might be thinking, well, the 2 pi cancels out and the L cancels out because L is a constant, R cancels out. Why didn't we cancel out at least the 2 pi L? Obviously, we can't cancel R before we do the integral because that would clearly make the problem incorrect. But why shouldn't we cancel out the 2 pi L before we perform the integral? The reason is, you'll notice that this 3/2 pi L r to the fourth actually gives us a representation for the Q free inside. Because that's in the first line, we haven't really tampered with anything. We've only manipulated that side. We haven't like transferred anything from side to side. That 3/2 pi L r to the fourth is the Q free inside. So that's going to be useful for us later on. Obviously, you could cancel out the 2 pi L before you do the integral, but that's going to give you more work in the next step, in the next region. So that's why I recommend not doing it. I recommend finding it like this, d times whatever, and then canceling it off the d, and then finding what d is. So when you cancel out the 2 pi RL to the right side, or shift it to the right side, I suppose, you get d equals 3/4 r cubed. And then it's very simple to turn that into an electric field. All you have to do is take the epsilon r coefficient of whatever region you're operating in. In this case, it's 2, because ER1 is 2, and you also divide by epsilon naught. And you also add a r hat vector. So this is our electric field expression for that region. Moving on, this region is the gray region. It's wherever the radius is between B and A, which are 2 and 1 millimeter respectively. So this is where the problem starts to get a little bit tricky. The only other thing that could even be remotely tricky so far in this problem that wasn't remotely plug and chug is the fact that for the first part the bounds were 0 to R instead of 0 to A. So now we do want to do 0 to A because we want to find, since we're like in the gray region, we can't just ignore the influence of the blue part. So we want to find the total influence of the blue part on our D field and then later on the electric field. So you'll notice that when we integrate from 0 to A instead of 0 to R, we essentially just get the right side of this expression being 3/2 pi LA to the fourth, and it used to be 3/2 pi LR to the fourth. Now, if you had canceled out previously, it would be a lot more confusing, but now you technically don't even have to integrate 0 to A. You can just replace the R with an A, if you see what I'm saying. But I showed the work here just because it's easier to understand if you show that you're integrating from 0 to A. This is the case where you do want to integrate from 0 to A. So what we're basically representing the D field in the gray region with is a sum of the old D field and the new D field. To find the new D field, we integrate from A to R, not from A to B. We integrate from A to R, as you'll notice. And once again, we do rho dV. The rho is different because it's the second region's rho. It's -5 over R. And the ADR is the same because the area of the cylinder is the same. It's 2 pi RL. And we're going from A to R. So we plug those in, then we do the integral, and we get d 2 pi RL equals -10 pi L times R minus A. So now we put those together. We get the part from before and we get the new part. And we set those equal to d2 pi RL. I'll give you a moment to look at it. Now you don't, obviously this is just algebra. You don't have to expand the R minus A. You could leave it factored. You could factor stuff, you could even factor more stuff out. You could factor out pi L. Well, pi L cancels, I suppose, but you could leave that factored. Like you could factor out the 5. But I prefer to fully expand it into as many terms as possible because we're graphing it later on and you want to be able to see the degrees very clearly of each separate term. You don't want it to be confusing as you work. So now we're doing the E field. The E field is once again the D field over epsilon r constant and epsilon naught. In this case, it's epsilon r2 since we're in the gray region. The epsilon r2 constant is 4 here. It was 2 in the first region, now this one is 4, and we have an epsilon naught on the bottom. So as you can see, you can put your solution for this part in terms of, not in terms of, but you can factor it more than I did here. Like you can factor out the epsilon naught on the bottom, you can factor out the 4 on the bottom, but I prefer to just have each term just be separate, and the only thing that's factored out is the r hat the vector, R vector form. So, or unit vector, I suppose. Now we're going for the region where we're outside of the cylinder, and you might be able to guess what we're going to do, which is essentially, for the first part, we went 0 to R. The second part, we did 0 to A plus A to R. Now we're doing A to B, and we're obviously including the blue part as well, which we still have, the 3/2 pi LA to the fourth, because that still affects the problem. So we essentially just do the same thing as we did before, where we do the same integral, except instead of A to R, it's A to B. Very simple. We get very similar answer, except we have a B instead of an R, I believe. And there we go. We cancel out the 2 pi RL from both sides. Boom, boom. We have a D field. Now, for this part, you might be asking, why don't we have epsilon r of any kind? Well, what is epsilon r when you're outside of the sphere? The epsilon r is 1 because it's defined as 1 for air. That's like the point of the constant itself. It's the ratio of the material of some property of the material to that property in air. So for air, it's the ratio of air to air, so it's 1. So the ER in the denominator is just 1. So all we do is divide the D field by epsilon naught and add an R hat, and we have our answer. So here I've written out all of our answers for every region, and I'm not going to go over graphing it with you, but I recommend just going to like Wolfram Alpha to try to learn how to graph these fast for a test, or you could use a graphing calculator too. Well, you should be able to use a graphing calculator, but you can also eyeball them. Um, so that's part A. We have the epsilon, the not epsilon, the electric field in terms of radius in all regions, and we graphed it. So moving on to part B, it's asking us if we placed that cylinder near a ground plane, can we use Gauss's law? So in long story short, we can't. If you'll remember, one of the prerequisites for using Gauss's law is that the it, it essentially needs to be symmetrical in terms of the the so the r hat vector that we used here isn't going to be symmetrical. Like if you try to draw r hat vectors pointing out, it's going to be different based on where you're pointing. If there wasn't a ground plane, it's the electric field is the same regardless of what like your angle is. But in this situation, the electric field's clearly going to be different. What if you're, you know, straight up from the cylinder, or you're to the right or you're to the left, it's obviously going to be different because the ground plane affects it. So you can't just come up with an expression in terms of R because you need to have other stuff describing it. So because there's no symmetry with this electric field expression or the D field expression, you can't use Gauss's law.